In this video, we are going to use the law of conservation of energy to analyze the motion of a falling object. So we've done this before using kinematics, but I'm going to show you how to use the law of conservation of energy, and it's actually a lot easier, and you can take into account things like air resistance and whatnot. So here's a cliff, and this cliff is 25 meters high, and we are going to drop a ball off the cliff, and our goal is to find the velocity of the ball right before it hits the ground, right down here. So find the velocity, final. So in the law of conservation of energy, we have a 5-step process. The first step is to draw the reference line. In the previous video with the crossbow, the reference line didn't really come into play because the object was not moving up or down, but in this one, it plays a major role. It's basically the line we measure all heights from. So actually, I go into the given on my diagram, and I draw a line, and I write it as RL. So all distances, vertical distances will be measured relative to that. Step 2 is a statement of the law of conservation of energy, which I write EA equals EB. More importantly, though, I actually go to my given and I write what A and B are. So I'm going to say A here is at the top and B is way down here at the bottom. So I'm clearly identifying my beginning and end points, which the law of conservation of energy is what we want to do, beginning and end point. Okay. In the previous video, you saw how we drew the buckets in. Each one of these buckets corresponds to a different type of energy. So if I drop the ball, it has a 0 velocity initially, so I have no kinetic. For this bucket here, the potential energy due to gravity, I ask myself, is it above the ground? Is the ball above the ground or the reference line? I would say yes, so there's some potential energy here. There's no elastic potential energy. I'm not shooting down with a slingshot or a crossbow, which I actually could do, and I could easily account for that. At point B, so it's going to accelerate due to gravity, and so it's definitely going to have some kinetic. Now, it's the kinetic right before it hits the ground. It's obviously going to hit the ground and stop, but this is the maximum velocity it attains. Um, when it gets to this reference line at the bottom of point B, there's no more potential and no spring or anything like that. And we're not going to consider air resistance here. Again, this is for energy that's lost in pouring the energy from this bucket to this bucket. That's what that represents. We'll address that in later videos. So my equation becomes mg height at A is equal to 1/2 mvb squared. So that's my equation. So step 5 is simply math. So I'm going to rewrite my equation here, mgha. And when I write this, you're going to notice that the mass cancels, which may seem odd at first, but remember that the mass of an object is independent of its acceleration rate. So I'm going to cancel the mass, and so I'm going to solve for VB. So VB is equal to 2GHB, and if I plug the numbers in here, this is 2 times 9.8 times 25 meters square root. And that answer is 22, I believe, approximately 22.13 meters per second. And you box your answer, and you're done. The one interesting thing about this, though, is when you use the law of conservation of energy, previously G was negative 9.8, and it still is, but when we deal with conservation of energy problems, we use the positive. And this arises because the way we define energies. So note to self, when you use when you're doing problems using the conservation of energy, use the positive value of 9.8, not the negative. And your final answer 22.13 meters per second. So in summary, it's a 5-step process. You draw the reference line, and as you saw here, that clearly identifies where we're going to measure distances from, specifically the 25 meters. Measure from this bottom level here. The second step is to clearly write the law of conservation of energy, denoting points A and B. Step 3, filling in the buckets. So you can conceptually see where energy is at the beginning and end point. From there, it's a one-to-one correspondence. We write equations for each term, and then step 5 is math. We need to solve for the appropriate variable. And so that's an example of using the law of conservation of energy for an object that's falling.